Hello everybody. It is a holiday today in Sydney. I hope you're enjoying the day wherever you are and whatever you're doing. I can see 11 people, 11 legends have joined us today. Hello everyone. Am I coming in loud and clear? Let me know that you can hear me okay in the chat. Excellent. Now, also, if you want to, feel free to switch your microphones on or cameras and you can say hello, give us a wave or a hi or something. We've only got 13 people, 12 or 13 people, so, it makes sense to talk and rather than, only use the chat, right? Okay, so the reason why I thought that we would do the lecture today is because, well, it's a holiday, right? But if we don't do it today, then I just need to record it another time. So I just thought, well, why not just do it today? So yeah, so the main idea that we're going to talk about today is the mean value theorem. So let me share my screen with you. This is a really important topic, and it's similar to the intermediate value theorem in some respects, but this is going to be the main focus of today's lecture. Okay, so let me know what's going on in the chat. Let me know if you have any questions or comments. So the first strange word here is the word mean, and what the meaning is average. So instead of calling this a mean value theorem, it's not nasty or angry or whatever. It's about averages. Okay, so in statistics, you talk about the mean of a set of data being the average, right? Here it's the same, all right? And what we usually abbreviate it to is the MVT. Yeah, Maximilian, we're doing calculus first. We are mixing it up today. Okay, I hope you're doing okay. Yeah, so we're doing calculus first today, just because I don't know why, but we just are. So yeah. So let me just see what's going on down there. Yeah, we're doing calculus, so it's on like Donkey Kong. If you know what this is, let me know in the comment section. All right, so mean value theorem. How does it work? What is it? Well, we'll learn about this, and there are two main applications of the mean value theorem. One is when you prove inequalities, and we'll look at some examples involving that. And the other one is when you're dealing with derivatives and monotone functions. So when we talk about monotone, we mean it increasing or decreasing. So monotone is just a word that captures either of these situations. Okay. All right. So MVT, you down with MVT? Yeah. You know me. And the easiest way to understand the mean value theorem is to draw a picture. Okay. So let me sort of see if I can put a picture in here. And suppose I've got a function that looks something like that. Okay, and the function is continuous on an interval like this. Say it's a closed interval. And it's differentiable, so it's got a tangent curve, right? Okay. What the MVT tells you is that if you draw a line segment joining these 2 points, right? then somewhere in the graph, the tangent line and this line are parallel. Okay, let me say that again. Take the endpoints and draw a little line segment. This MVT tells you that there's some point in between A and B where the slope of the tangent line is parallel. Okay, so if we look here, it might be like, I don't know, like here or something. Right? If I draw a tangent in there, you can see those two lines are parallel. Okay, so whenever I'm looking at the MVT, I like to draw a picture first before I write it down or try to understand any of the technicalities. There's a really easy special case of this. So this is like MVT. It's when f of b and f of a are actually the same value. So let me draw a picture with that. Let's say it looks like that. Okay. So here, f of a and f of b are the same. There's a, there's b. Okay, so the slope of the line joining the endpoints is 0, and there's got to be another point where the slope is also 0. Okay, so you can see those two lines are parallel, and it's a horizontal line, so the derivative is obviously 0 at that point. So that's pretty much, this is the general MVT. This is a special case called Rolle's theorem. Okay, so this is the general case. This is a special case that's useful sometimes. All right, so let's have a look at the MVT and see if we can understand what's going on. And I'll try to squeeze the pictures in here. All right, you assume continuity on a closed interval and differentiability on an open interval. The MVT tells you there's at least one number C between A and B, such that this is true, okay? So what is this? This is just the gradient of that line there, okay? It's this is the slope of the line joining that point to that point. And this is the tangent line, the slope of the tangent line to the curve at some point C. Okay, so for me, rather than remembering all of this, sometimes it's just easier to draw a picture and work it out there. Now, it's similar to the IVT because it's an existence theorem. It says there is or there exists at least one point. Okay. Okay. So it's like an existence theorem or whatever. All right. So, like I said before, a picture can help. MVT is similar to the intermediate value theorem. It's an existence theorem. The MVT, the one that we're talking about now, it doesn't tell you how many numbers C satisfy this. It just says at least one. And it doesn't tell you exactly where it is. It just tells you that it's somewhere between A and B. Okay. Now, so this is an amazing theorem, and it's very useful for doing interesting things with. And we'll have a look at some examples in a minute. I'm not sure, the proof is probably beyond this course, but you can kind of see from the pictures what's going on, right? If you draw a line from here to here, there's got to be some point where the slope of the tangent line has the same slope. These two things are parallel. Okay. All right, so it's a heavy-hitting theorem. It's probably something you haven't seen before. Like I said in this course, with the calculus, some things are familiar and some things are new. So I think this is definitely something that's new. So So let me know in the chat, have you seen the MVT before? Let me know if you've seen the MVT. I'd be pretty surprised if you've seen it before. Okay, so let me know. I said no, so thank you. If anybody's, let me know if anyone's seen it, because I would be really interested in that. Okay, so that's the theorem. It's got to do with the slopes of these lines. Now, another interesting idea here is you can relate, you can think of this, if f is like a velocity function, this is like the average velocity, and this is the instantaneous velocity, right? So another way of understanding the MVT is saying, well, there's some point where the instantaneous velocity is equal to the average velocity over the interval. Okay, so if you like physics perspectives or anything like that, then that's one way of kind of interpreting it. Okay, so average velocity versus instantaneous velocity. That's an interesting perspective. All right, so mean value theorem, MVT, super important. Yeah, Aria, absolutely. It's like the rise over the run, you know. So if you look back at this picture, you know, what is the gradient of this? Well, it's, you know, you work out the rise. The rise is f of b minus f of a. The run is b minus a. So it's exactly here like you're saying in the comments. Okay. All right. So let's try to understand this MVT a bit more. It's quite mysterious, right? It's quite mysterious. And so let's work through some examples and see if we can understand how things work. Okay, so I'll try to put this in here. All right, so here's a function, 2x squared, and here's an interval. Show that the conditions of the MVT hold. Okay, so what are the conditions of the MVT? There's two of them. F needs to be continuous on the closed interval, and f needs to be differentiable on the open interval. So there's only two conditions. Okay, and then it gets into the conclusion. So who can tell me in the chat, is this function continuous on this interval? And if so, why? Who can tell me? Who can tell me? Come on, there's 27 people here on holiday, right? Who can tell me in the chat, is this function a continuous function on this interval? And if it is, why? Okay, thank you, Joyce, Aziz, Aichen. Yes, Maximilian. Yes, so Aria, I like your comment too. So Maximilian basically says, look, it's a polynomial. Polynomials are nice friendly functions. They're all continuous. And Aria is saying in the chat, it's a parabola. So it's a nice, I guess you're saying it's a nice smooth curve, right? So I'm going to take that and see if we can make some comments. So f is a polynomial, and so is continuous and differentiable everywhere, right? So for all x, this is like the whole real line. Thus, 2x squared, it satisfies the conditions of the MVT on the interval 1, 4. Okay, so it's continuous on this closed interval, and it's differentiable on the open interval, right, where you don't include the endpoints. Now, why don't you include the endpoints? That's a good question. Why do you talk about differentiability on this interval and not this interval? Well, we haven't really defined what a derivative is at the endpoints. So this is enough for us. Okay. So the second part of this question, can you find a value of C that satisfies the conclusion? So we're actually looking for a C, a value of C. Can we find this C such that this holds? Okay, so let's see if we can find that. All right. So basically, we want to solve this equation for C. So we differentiate this, we let x equal C. So it'll be 4C. F of B is going to be 2 times 4 squared, which will be 32. F of A will be f of 1, which is just 2. And B minus A will be 4 minus 1. Okay, so let's simplify this and see if we can solve for our C. Sorry, 3. Okay, so C will be 2.5. Okay. So from these calculations, there's only one value of C. It's between 1 and 4, and actually it equals 2.5. Now, it's rare that you'll actually be able to find the C, and there's only one. But in this case, it's a nice sort of simple function here. So not too hard to actually show that the conditions hold, and then actually use this by the NVT to solve it. Okay, so let me just add another extra couple of things. So we're applying the NVT, so we know this is true, right? The sum C between 1 and 4. Okay, so that's an idea or an example showing the thought process that you need to go through in order to ask yourself, well, does this function in this interval really satisfy the conditions of the MVT? There's two conditions, right? Continuity on the closed interval, differentiability on the open interval. Okay, then you can move to this and maybe find the C. Maybe find the C. Okay. All right, let's look at a slightly different question. Now we're getting a really funky function, a more difficult one. Okay. So I'll bring GeoGebra up in a minute, but let's read the question first. Here is our function. Here is our interval. Show that there is at least one C. So by this we mean C is strictly between 1 and 3, where the derivative of our function is 0 at that point C. Okay. So let me go to GeoGebra, and we'll see if we can do an example here. So let me go over here. Okay, and I'll load it up. So here I've just used GeoGebra to plot the curve for x between 1 and 3. Okay, so who can tell me on the chat where's one point where that function has a 0 derivative? Who can tell me on the chat? Nicholas, yes, you can see. Thank you, everyone. You can see down here that obviously there's a turning point there, right? Or a point where the derivative is 0. And there might be another one sort of around here somewhere, right? And maybe another one over here. So from the graph, it looks like there's 3 places where this function has a 0 derivative, and you'll see the endpoints are the same. Okay. All right. So let's work through this and see if we can solve this problem. All right. So back to my document camera. So is this function continuous on that interval and differentiable on this interval? The answer is yes. It's like a composition of continuous and differable functions. So this is my shorthand for differentiable. Whose composition okay, so x minus 2 all squared is a polynomial, and therefore it's continuous and differentiable. This is also a polynomial that's continuous and differentiable. And when you take the cosine of that, the whole thing is continuous and differentiable. So when you multiply everything together, the whole thing is continuous and differentiable. Okay? Hence, f satisfies the conditions of the MVT. All right? So you might want to write more or less, it's up to you. Okay? So thus, there is at least one C. So the ST stands for such that. So for B equal 3 and A equal 1, what we're going to do, if you put those things in here, you're going to get 1 cos 1 for the first part, and you get the same for the second part. Okay, so you get 0 over here. All right. So there you go. We've actually got it from the mean value theorem. All right, Maximilian, good question. Is it enough for us to say continuous based on graph to conclude if a function is continuous or not? Let me think about that for a while. I think what you would need to do, Maximilian, if you were saying that it was based on the graph, you'd have to include the graph, right? So if you were doing this in your final exam and you're asking for a graph, the person who's marking your work would want to see the graph. So it might not be so easy to produce that. Okay? Does that make sense? Yeah, yeah. But if you do have a graph, then of course, you know, you can use it, right? So that's it. So you stop and you say, I checked the conditions of the MVT held. Then I went through and actually used this relationship with B equals 3 and A equals 1, and that's your F. And the top bit cancelled out, and so you know that this must equal this for at least one C. Now, from the graph, if we wanted to add something else, there are actually 3 points C where. Okay, But we can't determine that actually from the mean from this relationship, right? So we're not actually differentiating that and then solving it. We're just using the MVT. All right. So that's a more complicated question than the previous one. Let's bring it up a notch now, and we'll talk about the third part of this lecture where you want to prove inequalities. And this is probably the main part, the most important part, okay? Because this is where you're actually taking the MVT and you're doing something with it, right? You're actually doing something with it. Okay, so you'll see a lot of questions like this in your either in your tutorials or in your course pack, or maybe in some of the assessment, okay? And it gives you a little hint. Apply the MVT to prove this inequality holds for all positive values of x, okay? So let's actually see what this looks like as a picture first, and then we can move to the solving it, right? So let me share my GeoGebra. Did somebody say GeoGebra? And here I've got my logarithm function, and here I've got my x function. Okay, and you can see for along the positive x-axis, the grey logarithm curve is always below this this y equals x curve. Okay, so they touch at one point at 0, but then this one increases faster than this one, than the grey curve. Okay, so you can kind of see that it's true, and we kind of know where we want to go, but how do you use the MVT to do this? Well, I'm glad you asked. I'm glad you asked. So let us show you what is going on here and how we use the MVT. Okay. So the first thing I'm going to do is realize that, well, if I move this around, then showing this is equivalent to showing that this function is positive for all positive x. Okay, so I'm going to introduce a function and try to keep things as simple as possible, right? So move that over here and define a new function and show that this is true, but this is positive, right? Okay, so now here comes the weird thing, right? I'm going, this function is continuous for all positive x, and so is this one. Okay, so our f is continuous and differentiable for all x positive, right? And so the two conditions of the MVT hold. Okay, so we've got that out of the way, and what we would like to do is actually now just go through and apply it, right? But, and this is important, we do this application in a special way, and the biggest number of questions that I have is about the notation. So I'm going to show you some notation for this, and hopefully it's clear. But if it's not, just pipe up in the chat and let me know. We'll turn the microphones on because it's something that's very different. All right. So consider now, what should I do with the notation? I'm switching to a new variable now, and you'll see why I do that in a minute. Okay, so what I've done there is I've switched to a new variable and I've put x in the interval of interest, right? And x is still positive here, of course. Okay, so what I'm trying to do here is set up a function that comes up with this sort of thing, right? So that in this case, the b is going to be my x, the a is going to be 0, and I'm going to get something involving f of x in here when I actually apply this. The t is going to be is going to disappear, right? Because I'm going to sub in that, and that, c, right? So the actual t here is totally going to disappear. So don't worry about the like placing the t in here. We do this so that we're actually going to get back to the x's. All right. All right. So let's do it. By the MVT, what do we know? The derivative of this at c equals this, where you work that out from the endpoints. Okay. Okay, so c is positive but less than x. And so what you do now is you work with this. So differentiate your f, put in t equals c, work this out, and that's what you actually end up working with to come up with this. Okay, let me show you. Okay, so if you differentiate this, you're going to get 1 minus 1 on 1 plus t, and at t equals c, you get this. So this is just that differentiated, and you replace t with c. Okay, f of x, well, just go in there and replace t with x. Go in here and replace t with 0. Okay, that's just going to be 0. X minus 0. So it looks quite complicated, but these things are going to simplify, right? That's just 0. And now, let's put this over the other side. We'll get x minus log 1 plus x over x. Okay, so I'll just sort of switch these around. Okay, I want to work on this. Okay, we're almost done. I know it's been a long question. What we have to do is do something with this, right? So form some sort of inequality. Now, there's a few that you could do. You know that 1 on 1 plus c for all c positive is between this and this, right? Okay. For all c positive, this is an inequality. So what you can do, you can say, aha, this thing here is always going to be greater than 0. So now you've got the critical step that you formed an inequality, and you know that this left-hand side must be positive. So if the left-hand side is positive, and that's positive, it means the top bit has to be positive. So that is, just move that around. Okay, so not an easy problem. Maximilian, good question. So do you mean this one or this one? The first inequality or the second inequality, Maximilian? Let me know. Yeah, so from here, if you take away 1 on 1 plus c from both sides, right? So, okay. You just take away that from that side, move it over here, and that becomes 0, right? You got it? Yeah. Okay. So good question. So quite a long question, and the key thing is to come up with some inequality that actually gets rid of or manages away the c. Okay, so you're just left with some sort of nice inequality that you can use, right? So if we know that this is positive and the bottom's positive, the top bit has to be positive. Okay. So not an easy question. But the method for these kind of problems are usually the same, right? You define a new function, you check that the MVT conditions hold, and then you introduce this new variable t, and you apply the MVT, and you need a basic inequality. Okay, so I know it's a holiday, and but this is probably the most important example that we're going to talk about today. Okay, and this is of course for positive values of x. All right, so let me know what's happening in the chat, people. Is there anything you'd like me to repeat or go over, or okay, there's something in the chat. It was a pretty interesting process. What some students think, well, does this have to be my function? You can define your function in a few different ways, but the most important thing is that you want it to work, right? You want it to work. Okay, the last part, Serena, where would you like me to start? There's final line, second final line, third final line. Which one? You tell me. Or you can just turn your microphone on. Yep. So we've simplified this, we've simplified that, and then we've switched these things around. So that is the same as that, that is the same as that, okay? So what we want to do is get rid of this c somehow through an inequality. Now we know if you draw any graph, let's say 1 on 1 plus c, where c is positive, it always stays between 0 and 1. Okay, so if you move that around, you'll get that. So this is positive, so that's got to be positive. So now you've got the inequality that you can work with. Okay, so you've got a fraction that's positive. Well, the bottom's positive because x is always bigger than 0. And so if the bottom's positive, the top has to be positive. You just rearrange that. Okay. Yeah, Maximilian, C is positive because C is between 0 and x is always positive. Exactly. Yep. Okay. So here, C is positive. Yeah, that's good. So you've sort of got two things, right? You've got the x's and then you've got the c's between 0 and x, and it's strictly between. So, whew, that's quite a difficult problem. Okay, quite a difficult problem. So don't worry if it's not particularly clear at this point, but you will see a pattern. Okay. There, mamma mia. You will see a pattern. Okay. And sometimes it's just some trial and error. This is the Lego professor, apparently. This is apparently what a Lego professor looks like. Hello. I like the MVT. So don't worry if it's not particularly clear, but the steps are usually the same. Okay. So let's do another example, and hopefully the second example will give you some more insight. Okay, so let me move on to the next example. Oh, come back. Yeah. All right. So here's a classic example. This is one of your tutorial problems, actually. So apply the mean value theorem to prove that sine x is less than x. Okay, so let's go to the GeoGebra again, and we'll see if we can plot this in GeoGebra. So here's the x function, and here's the sine x function. So you can see for x positive, right? For x positive, the sine function just goes between -1 and +1, whereas the x function just goes off to positive infinity. So we definitely know it's true, and the two functions touch at the origin. Okay, so we definitely know that it's true. So how do we do it? What does a solution look like? So let's go back to my document camera. Similar idea to the previous problem. I'm going to let my function here be x minus this, and we'll just try to show that it's positive. Okay. So I'm going to let f of x be x minus sine x. Okay, so is f of x positive for all positive x? That's kind of what I've transformed the problem to. Okay, so now what we're going to do is check that this function basically satisfies the conditions of the MVT. Well, x is a polynomial and sine x is a nice smooth curve. So together they will both be continuous and differentiable everywhere. Okay, so just like we did here, we would write a line with this one saying our f is continuous and differentiable everywhere. So by that I mean it's continuous and differentiable for all x on the real number line, right? So the conditions of the MVT hold. So that's good. Okay. All right. So what does that mean? Well, it means that we can use this kind of relationship to help solve or at least get our problem going, right? So I'm going to solve this in two parts, okay? And you'll see why I need to do that in a minute. So yeah. Okay, so I'm not going to worry about the whole real line yet, or the whole half line where x is positive. I'm just going to do it on this interval first, and you'll see why I'm going to do that in a second. Okay. Hang on, sorry, I need to introduce the new variable. Okay, so the x here is going to be less than or equal to 2 pi. All right. So I'll just move that down. So by MVT, we know okay. for some C, at least one C. So let's work this out. All right, so let's differentiate our function and put in t equals c. So it's going to be 1 minus cosine c, right? If I differentiate that, I get 1. If I differentiate that, I get cosine, and I replace it with c. Okay? And now for this one, it's going to be x minus sine x at that end, and 0 minus 0 at the other end. Okay? So this is going to disappear. Okay? Now, just like we did in the previous example, it's time to come up with an inequality. Okay? Now, we're just working on this interval here. Okay? Okay, so x is between 0 and 2 pi, and c is between 0 and x. So what you can do, you can say, right, 1 minus cosine of c is going to be positive. Why is that? It's because cosine c is less than 1. Okay? If c was equal to 2 pi here, you wouldn't get that inequality. You'd have to have a greater than or equals to. Okay, so by restricting our attention here, we can actually get the thing we want. All right, so you've got something that's positive. The bottom's positive because x is, that's the interval we're working on. And that means the top must also be positive. Okay, haven't finished the problem yet. We've only shown, so we applied the MVT on this interval. We haven't got it for the whole line, whole half line yet. How can we do the second part? Second part is easy. Okay, the second part is much easier than the first part. Okay, so for x greater than 2 pi, so let me just draw a little thing down there. So let's consider x minus sine x. Now, x minus sine x, if x is greater than 2 pi, that's got to be bigger than 2 pi. And that's bigger than 1, right? So this difference here has to be greater than 0 because sine of x is between -1 and 1, right? So combine 1 and 2. So I squished it in the bottom. Okay? So two parts to that question. The first part, we actually applied the MVT. We were a bit strategic with our interval choice. And the reason was, if you don't restrict the interval there, you can't get the strict inequality. You can't get the greater than. It would have to be a greater than or equals to. Okay? So we did it on that interval. And then for x bigger than 2 pi, it was a super easy calculation. And you just combine the first case with the second case. Yeah, Bill is down with MVT. He's down with MVT. Yeah, you know me. Hello, Alan. Good morning, Bill. How is everyone doing out there? Okay, so this is probably at the very top of the difficulty scale, a question like this. You can probably do it a few different ways, but this is the way that I do it. Instead of going for the whole thing first, break it up into two parts, okay? But the structure is the same. Check the conditions of the MVT. Then use your MVT equality to form some sort of inequality and get the inequality that you want, okay? So not easy, but manageable if you practice and think about what you're doing. Okay. All right. Last part of the class today. Monotone functions. Monotone functions are, like I said at the beginning of the lecture, when we use the word monotone, we just mean they're increasing or decreasing. This is like a collective term for either of these functions, okay? So here's a definition for increasing and decreasing functions on an interval. So if you have sort of this function here, you would say, okay, well, sort of looks like that, right? So if you take any interval here, and you have, say, a point A there and a point B there, then the value of the function at B is always bigger than the value of the function at A. Okay? So again, we see the inequalities, and this is essentially what it means, right? So as we move from left to right, the function, the values of the function are greater than the ones on the left. Okay? All right, folks. Last question. And again, this is, I think this might be in your notes, but I think it's an interesting example because it connects the MVT with the idea of increasing or decreasing functions. Okay. All right. So let me just add something in here just to sort of set the scene a bit better. So suppose you have a function that is defined on this closed interval. And let's make IB the open interval, AB, okay? We want to prove that if the derivative is positive for all points in this open interval, then f is an increasing function on that interval. Okay, so how do we do it? Well, let's use the MVT. Okay, so since f is differentiable, it is also continuous, right? We talked about this relationship in previous lectures, right? Differentiability implies continuity. And so combining these two things, we can apply the MVT. Okay, so the MVT is applicable. And so there is at least one point C, which is between A and B, such that this holds. Now, what do we know about all the derivatives? They're always positive by assumption. Okay, so this, we know that's true for every x in the open interval, and c is one of those points. So this has got to be positive. So we get this. So again, we've got a fraction that's positive, and the bottom's definitely positive because b is greater than a. So we know that for all a less than b, f of a is less than f of b. By the definition, f is increasing on our interval. Whew! Maximilian, ST is such that, okay? ST such that. Okay, so when I write ST, so there's another one here on page 6. Hoo-wee! So that is quite right at the top of the tree in terms of difficulty. So this was very difficult because you had to prove something. This one was, hang on, let me just find it. This one was difficult because we did it in 2 parts, right? This one was easier because it was a bit more straightforward. And these ones were super easy. So that's kind of the level of difficulty. So don't worry too much if it's if you're finding the MVT a bit strange or like a little bit hard to understand. Remember, you can always go back and draw a picture, and it's just got to do with the slopes of these, either the tangent line or the points joining the line joining the endpoints, right? Hoo-wee! Oh, I'm exhausted, and it's a holiday. Anyway, yeah, look, let me know your questions in the chat, people. MVT is not easy, but let me know what's going on. See if I can help. I'll hang around for a few minutes before I pass over to Captain Bill. But let me know what's happening, people, in the chat. I always get worried when there's no chatting because I'm not sure if people are understanding or not. Okay. So, what is up, people? Let me know what is going on in the chat. It's been quite quiet today. All right. Let's go back. Okay. So 10 points if you know what this is. Hey. Let me know what you think it is in the chat. Oh. Nicholas. I'm impressed. How do you know it's a quokka? You're absolutely right. Really, is it? Okay, kick those people off. Hey. Quokka. They're clearly the best. This one's from WA, as you would probably know. Good spotting. They are the best. Look at those claws though. Like, that would do some serious damage, I reckon. Watch poor old Mario, no match, even with a mushroom. All right, folks, I will say goodbye. Enjoy the holiday if you are having a holiday. Enjoy Captain Bill's lecture, and I will throw over to Bill. Have a break, and yeah, take care, everyone. I'll see you on Thursday. There's no tutorial today in my class, but I might see you Thursday. All right. Yeah. Have a great day, everyone. Alan, Lee, Menglu.